world is changing fast. New technologies are impacting how we think about products, services, and the way we live our lives. Nowhere is this trend more present than in financial services, where new business models and customer expectations are changing our conceptions about banking, finance, and the very nature of money. Welcome to Rebank, a visionary podcast about banking, fintech, and the future. The future of banking is here. Hello and welcome to Rebank. I'm your host, Will Beeson. Today we're thrilled to be joined by Scott Crowder, Chief Technology Officer of IBM's Quantum Computing business. In March, IBM announced IBM Q, an industry-first initiative to build commercially available universal quantum computing systems. IBM Q will enable customers to access quantum systems and services via the cloud. The technology will sit alongside classical computing solutions like Watson, IBM's artificial intelligence engine. IBM's progress in quantum computing mirrors advances by other institutions, all of which will no doubt contribute to quantum computing having a meaningful impact on businesses and consumers in the coming years. If you like today's show, please subscribe on iTunes or your podcast platform of choice and leave us a review. Thank you very much for joining us today. Please welcome Scott Crowder. Scott, welcome to Rebank.
Thank you, Will. Happy to be here.
To start, would you mind giving us a general explanation of quantum computing to make sure we're all up to speed?
Sure, I'll try to do a short version. So quantum computing is a very different beast than the classical computing that we're used to. Quantum computing relies on some very interesting quantum physics to create just a completely different way of processing information. Quantum computing, universal quantum computing, leverages this concept of superposition, which means that instead of having a quote-unquote normal bit like we're used to in classical or when we're counting on our fingers of something either being a 1 or a 0, in quantum computing, you're leveraging the fact that the state of your bit can either be a 1 or a 0 or something that is at the same time a combination of 0 and 1. And that allows you to manipulate the information that you store in those bits in a very different way. To make things even a little bit more complex, quantum computing also allows you to entangle two bits. And this is a quantum property that only exists, in the weird world of quantum physics, which is the world we live in. We just don't recognize it, where independent particles aren't really independent. They really have dependence on each other. And this is called entanglement. And you can leverage this in a quantum computer so that the 2 qubits in a system, or 50 qubits, or how many qubits you've got, interfere with each other. And by leveraging that interference, you can do wonderful things with a much lower number of bits than you can do in a classical system. So the probability space you can explore scales exponentially with the number of bits because the bits are not independent and they can interfere with each other.
Okay, so you effectively have almost more variables that you're able to play with at the same time to kind of make calculations in, as you say, an exponentially powerful way.
Yeah, and it's the simple example that we always give on the power of exponential or the challenges of exponential scaling is this story, apocryphal story of a guy invents chess or checkers, and there's 64 squares on the board, and the emperor loves the game and says, name anything in my kingdom that you want, it's yours, just name your price. And the guy who invents the game goes, I just simply want 1 grain of rice on the first square, and then for every square after that, just double the amount of rice. And the emperor, not being a math major, goes, wow, that's a great deal. And after the first week, he's only given the guy 127 grains of rice, so he still thinks it's a great deal. But by the time he gets to the 30th square, he has now given the guy as much rice as it takes to feed his entire kingdom. And by the 64th square, you would need as much rice as the entire mass of Mount Everest. So, there are a lot of problems in the world that have this kind of exponential scaling. And classical systems, or classical computers that we're used to, or our fingers, as you count on fingers, scale linearly. You got 10 fingers, you can count to 10, right? But quantum information science allows you to take those bits and scale them exponentially. So you can solve or have the promise of solving those types of exponential problems.
And I think you mentioned quantum entanglement before. Is this Einstein's spooky action at a distance, this concept of kind
Yes.
of pairs of particles immediately reflecting the state of the other?
Yes. Yes, exactly. So we're basically leveraging what freaked out Einstein and has been proven to be real. That's just the way the world works. We don't notice it because we're not operating typically in a quantum state. And leveraging that for information science, and that's the thing that gives you this exponential scaling of your quantum system if it's a universal quantum computer.
Yeah, so you've referred to universal quantum computing a few times. That seems to be an important distinction.
Yeah, there's a lot of kinds of things out there that leverage quantum physics to do things, and there's kind of two types of quantum systems that are now being explored. One of them is called a quantum annealer, which is really a single function system. So it's a system that does one algorithm, and if you can map your problem to that algorithm, you can do it. I mean, it's like some people have made an analogy of it like it's an ASIC or it's a tabulator or a single function machine. A universal quantum computer is more like the computers that we're used to that you program, and in principle, it could do any operation. It's universal. It can run any kind of algorithm. Now, it's going to run some algorithms better than other algorithms. So in practice, you wouldn't run anything on it. But in principle, you could run anything on it. And you program it just like you would program a classical computer by basically giving it different instructions and then it being able to, based on those instructions, build out any kind of algorithm.
So are there some types of problems that quantum computing is better at addressing than classical computing or than humans? Or is the expectation that quantum computing is fundamentally better than classical computing in every single way?
It's not. What it's good at, and what initially it's going to be used for, is to augment classical computers in those types of problems that classical computers just don't do a very good job of. And it's those problems that are exponential. It's those problems that scale exponentially. So one class of them is just quantum physics, because quantum physics is that exponential problem we were just talking about. Particles interfere with each other in what you labeled as the thing that freaked Einstein out or made Einstein very easy. But that's how particles really work, like in a molecule. All the electrons are not independent. The electrons are interfering with each other. So you can't calculate the overall energy of a molecule by taking each of those electrons individually. You need to be able to have all the cross terms of them all interfering with each other. And when you have a small number of electrons, it's a tractable problem on a classical computer, but it's an exponential problem. So once you get to the point where you've got 30 electrons, 40 electrons, you're way beyond what a classical computer can handle, because it's now 2 to the 40th in terms of the size of the problem, and that's bigger than any supercomputer in the world once you get to like 45 or 50. So new materials development, anything that has to do with quantum chemistry, those are exponential problems that a quantum computer holds a promise to being able to solve that classical computers really struggle with. Mm-hmm. But there's also a lot of optimization problems that have that same characteristic. So, if you think of traveling salesman type problems, or something called the knapsack problem, in your brain, it seems like a fairly simple problem of, a salesman needs to go to 3 different stops and then go home. So what's the optimal order of those 3 stops to go and go home? It seems like a fairly straightforward problem, but that actually is an exponential problem. If you're just making 3 stops, there's not that many different combinations a classical computer would have to chunk through in order to find the best one. But if he has 50 different stops to make or 100 different stops to make, the number of possibilities that he has to go calculate in a classical computer goes exponential with the number of stops. So a classical computer just sucks at that. It's just not very good at that kind of problem. So there's a lot of logistic problems. There's a lot of financial optimization portfolio problems that kind of have that kind of same characteristic, that they're really exponential problems. As you add the number of variables or the number of states that are interdependent, the problem goes up exponential.
Can you tell us a bit about IBM's work in quantum computing to date, and then also maybe discuss the announcement that you guys made in March about your new 50-qubit cloud-based quantum computer?
Sure. So, IBM has been, doing quantum information theory for a long time. Charlie Bennett, who's, IBM researcher, was in this at the very beginning. There was a famous in quantum information science famous conference co-sponsored by IBM and MIT, in which Feynman basically, laid out we really should be doing this quantum computer thing because the world is quantum, damn it, and this is a very interesting problem, and quantum computing holds the possibility of solving these types of problems. So we've been doing it for 30 plus years. We've been making a lot of progress, but in the last couple years, the rate of progress has dramatically accelerated. And starting last May, we put out on a public cloud something called the Quantum Experience, which is a very small but real quantum computer with 5 qubits that anybody can log in, sign up, and start running problems on a real quantum computer, which has been amazing from an educational point of view and an academic point of view to actually let the world have access to real hardware. But the other thing that it taught us from a commercial point of view is that we actually know how to operate a real quantum computer as a cloud service for a long period of time. And that's not a trivial thing. You need to calibrate the system daily, make sure that it stays optimal in terms of its decoherence time and in pure working order for a long period of time. And the fact that we did that for almost a year now, gave us a lot of confidence that as we're building larger systems, we know how to operate them stably, keep them running, which allows us to commercially offer them. So we're going to continue to offer that free public access quantum experience for academic and educational purposes, but it's very important for us to grow the real use cases, the real algorithm development for quantum. So we announced in March that we're also launching a commercial program with the intention to build systems for a couple key early access partners starting this year, and then grow them to higher scale systems on the order of 50 within the next few years. So those two things were kind of at the heart of our March announcement: the continual improvement of our quantum experience, and then our intent to start commercially offering systems with key partners.
So you mentioned there that in the past few years, important progress has been made in quantum computing, despite the fact this is a problem that's been people have been working on for decades. Is there anything in specific, in particular, that's driven that advancement in the past few years?
Yeah, I think there's a couple things that come together. I think from an industry point of view, the quantum processor itself needs to be extremely cold because you need basically no noise or no interference other than the interference you're trying to put in there between the two bits that interfere with each other. So no thermal noise, no electrical noise, et cetera, et cetera. So on the thermal noise side, it needs to be at temperatures well below outer space, 15 millikelvin kind of temperatures. And the advancements that companies have made in dilution refrigeration to enable you to keep something that cold for a long period of time, in a kind of turnkey solution, has been really an enabling technology. But in addition to that, companies like IBM have made a ton of progress in getting the quality of the qubits improved to the point where they can, have a decoherence time that's long enough to allow you to run, many operations on that while it's still in a quantum state. So it's a combination of enabling technologies like dilution refrigerators that got much better, plus the quantum pieces of the technology themselves have really gotten a lot better in the last, they've been getting better year over year, but now that the decoherence times are long enough that you can practically do real problems on it. So it's a combination of those two things.
Gotcha. Can you describe the quantum experience, the IBM Quantum Experience, in a bit more detail? So how do people actually engage with it? How do they use it? And to the extent you can, what sort of problems are they addressing with it at the moment?
Yeah, so it started out last year as really being very much just educational. And It's available on IBM Quantum Experience. If you just put that in your favorite search engine, and you can just get to the site very quickly. Like I said, it's free, it's public. Initially last year, it started out as a drag and drop. So it was meant for educational. So if you had one of the few quantum information science textbooks, and you looked at the types of operations that you can do on a quantum computer, it was a very graphical representation that allowed you to drag and drop the gates you would find in a textbook on a real system and on a simulation, so you could simulate it, see what it does in perfect theory, and then run it on a real system, see what it does on a real system very, very quickly. And what's remarkable to us is that people have 15 publications and counting manually dragging and dropping icons to create these circuits over and over and over and over again by hand to create 15 research papers on a variety of topics. Some of them proving Bell's inequality, basically proving the thing that freaked out Einstein is real, all the way through better visualization to actually running real kind of very simple algorithms and use cases on it, Fourier transforms, optimization problems, things like that. Mm-hmm. But we recognized that we needed to get people more powerful and more programmer-friendly ways of interacting with the system. So the other thing in March we announced for the Quantum Experience was basically a language that people could actually program in, as opposed to dragging and drop icons. So as we enable them to simulate or use larger systems, like up to 20 qubits, that it makes it easier for people to programmatically type up the instructions and the algorithms that they want to get done. But we also have put out basically an SDK that's based on Python notebooks, which allows people to, via an API, call the system. So now you can actually write real programs that intersperses those quantum instructions with classical instructions, so you can run steps A, B, C on the quantum computer, get the results back, and then manipulate the data with a couple classical routines, and then send another burst out the quantum system to run 1,000 shots of this routine, and that allows people to build more real algorithms in a much easier way using software tools that they're used to, right? Python and Jupyter notebooks. Mm-hmm. So we're enabling people to start really building algorithms now, as opposed to just educational. So that's kind of like the next wave that we're doing from a quantum experience point of view. And then obviously, as we're enabling even more powerful systems for our early access partners, enabling them to use similar tools for them to grow the ecosystem of algorithm development.
No, I think it's a really, really interesting point, and potentially a key one looking longer term. This kind of union or fusion of classical computing and quantum computing, and building applications that incorporate pieces of both. If you look longer term, and given your expectations around the continued development of quantum computing, would you see that as a natural structure longer term, an integration of classical and quantum in day-to-day applications? Or do you think that over time that fusion starts to look different, that perhaps quantum computing starts to play a more important role in the actual building, deployment, use of applications that people and companies are using on a day-to-day basis?
Yeah, I think the way to think about it is that classical computers are really good at processing large amounts of existing data and storing large amounts of data. Quantum computers, for at least my lifetime, will be really good at doing those exponential problems, but not good at processing large amounts of data. So you can think of the quantum computing being a small amount of data in, explore a very large exponential space, so 2 to the n, and then collapsing back down to a small amount of data out, relative terms. Whereas classical computing is very good at processing in parallel large amounts of existing data. So for my lifetime, I think you're going to see in real applications a combination of classical computing doing the storing of lots of data and the steps that process lots of data, and quantum computing doing the steps that look at a very large probability space, look at what are all the possibilities and what's the best possibility kind of problem, whether that be in quantum chemistry or whether that be in financial portfolio optimization or logistics optimization or that kind of thing. So as far as, in my opinion, for at least the next 50 years, quantum and classical are going to be working in concert. Quantum is not going to replace classical computing, it's going to augment it.
It must be a fascinating time to be working in something like quantum computing that's kind of transitioning from academia to commercialization. And I would imagine that for different reasons, different types of organizations are helpful for advancing technologies at different stages, and that historically maybe more research type institutions, academic institutions were involved in very early stage development. And as we go, we'll start to see more and more commercially motivated organizations getting involved in kind of scaling this technology. What are some of the main institutions that have done work on quantum computing to get us to where we are? And how would you expect to see that develop going forward?
Yeah, so I mean, you've got a bunch of academic institutions and research institutions across the globe, like Delft in the Netherlands, Waterloo in Canada, MIT, Yale, Santa Barbara, et cetera, in the U.S. from an academic point of view, plus a bunch of industry participants like IBM and Microsoft and Google, plus startups like D-Wave and Rigetti. So there's been a lot of people working on it. I think you're absolutely right. I mean, I think we're still at the stage where you've got both push on the science and the research, but we're at the point now where we're starting to need folks with use case domain expertise to understand, the problem that you're trying to solve and how you develop quantum algorithms to, enable you to solve problems that you could never solve before that have real world applications, whether it be like drug companies or materials companies wanting to understand how to leverage this for quantum chemistry, financial institutions wanting to leverage this for portfolio optimization or risk analysis or whatever, car companies, retail companies, et cetera, wanting to look at this from a logistics oriented or route oriented, large complex system designers looking at it for how do I improve my software quality and large complex systems. So again, those exponential problems, but we're at the point where we need to engage the domain experts who would see a very large first mover advantage if they can leverage this technology before others in their industry to get 5% better portfolio optimization is a big deal for certain financial institutions, or getting a 2x better solution from a logistics point of view would be a huge deal from any companies that are logistics oriented, and similar for drug discovery materials, et cetera, et cetera. So we're at that really exciting time where you've got the need for both early industry participation as well as still the core science, core math, core research and development. So that makes it a really exciting time. And why our focus is really on, even on the commercial side, our focus is on building ecosystem of algorithm development and use case development, because we really believe that's going to be the limiting factor in progressing the technology. More than anything else at this point is algorithm development. So when we go and look for our early access partners and when we announce them, they will be those folks who not only are interested for themselves, or not only interested in it from a science point of view, but also interested in building an ecosystem of industry use cases to help drive that algorithm development.
So I suppose just so everyone's on the same page, when we talk about algorithm development, we're talking about effectively ways of deploying this power to solve real business problems.
Exactly. Like, the algorithm you use to simulate a molecule's energy state, or the algorithm you would use to solve a max cut or knapsack problem. Those basic algorithms that over time, then developers higher up the stack could just, like they're used to today, make a library call to go, run that type of algorithm. Where we are in the stage of development now is we need those algorithms to be developed so that in the hopefully not too distant future, the higher order developers can just go make a library call to, I want to optimize logistics route using this type of algorithm, just make a library call to that algorithm.
So is IBM actively engaging industry practitioners at this point to start developing things like that?
Yes, a couple different ways. Obviously, there's industry participants on the quantum experience from an educational point of view. We have something called the Frontiers Institute, which is kind of industry partners with IBM research to explore a bunch of topics, but quantum and quantum algorithm development is one of the key topics in that institute. And then, as part of our commercialization effort, we're clearly reaching out to potential industry partners as well as research and academic partners. We've recently had an open house for people in the industry who are interested. So all of the above.
I think it's interesting, this initial deployment mechanism via the cloud, i.e. build a quantum computer somewhere, offer people remote access to it to kind of do their processing from wherever they are. Do you expect that to be a longer term model that's adopted and used, or do you expect over time quantum devices to become more diffused, more kind of readily commercially available?
It's hard to say more than 5 years out, but I would say for the next 3 to 5 years, the hosted cloud model is probably the right, and that doesn't necessarily mean public cloud. It could be a dedicated system that's accessed via the cloud, as opposed to a public internet. And the reason for that is just quite frankly that the improvements in the technology are happening so rapidly that there's a lot of value for people to be able to get access to the most advanced quantum systems. We're at the stage of we envision like a major system upgrade every year. So we're not at the stage yet where you've got a 5-year depreciation cycle for your x86 server, and you're going to use that server for the next 3, 5, 7, 9 years or whatever, right? So because we're making improvements so rapidly, my personal opinion is over the next 5 years, this hosted model, cloud model, really is the one that makes most sense for users, so they have access to the latest and greatest.
So I suppose when one reads headlines and news articles about advances in quantum computing, a lot of it's around the number of qubits that various devices have. Is that the right place to focus, or are there other components that are important in kind of judging and understanding the capacity of these sorts of devices?
Yeah, no, this is really important. It's absolutely not the right metric. I mean, it's one of the important metrics, but not the right metric. And we're early days, so we're in the middle of trying to get to shape. What is the equivalent of operations per second that you would have in a classical system, right? Because it's not transistor count in a classical system either, right? It's the number of operations you can do per second. That's typically the metric, whether it's a storage system or a processing system. In a quantum world, like we said before, it's about the number of possibility space. So what the mental model is, how many possibilities can I explore in this system? So what's the volume of space that I can explore as opposed to the operations per second? That's really the metric that you should have your head around about how powerful a quantum system is. So we're calling it quantum volume, and we put out a paper which is trying to establish the framework for a benchmark, and we're looking for feedback, obviously, because this is early days, to improve on it. But it's more than just the number of qubits. It's also basically how many operations you can do on those qubits before they lose their quantum state. It's the connectivity. So how easy is it to move the entanglement around in your system? And it's also the gate error, because overly simplistically, if your gate error is 10% or 0.9, and you do 5 operations in a row, 0.9 times 0.9 times 0.9 times 0.9 times 0.9, you're very rapidly back in the noise, right? In the 50% probability. So your gate error is a very important metric in the capacity of a system. So you put all those things together, you get something, this benchmark that we called quantum volume, which again is what's the possibility space that you can explore on a given system. Now, qubits is a very important metric in that, because that's kind of the number of qubits is kind of your upper bound on how much probability space you have. But if you have 2,000 qubits and you can only do one operation on them, before you lose your coherence, and they're not well connected, and your gate error is 50%, then your quantum volume is basically zero. So it's not just the qubit count.
What are the greatest outstanding technical challenges that are still kind of being worked through at this point?
I think the gate fidelity or gate error is probably at a system level is probably the largest challenge, and improving that, getting it from 99.9% to 99.99%, and et cetera, et cetera, et cetera. So as we scale the size of the systems, if you don't, to the point we just made in terms of quantum volume, if you don't continually to improve that error rate and get it down, you can have larger systems, but you can't really leverage them effectively. So I think within the system, that's probably the biggest technical challenge. Outside the system, it's the algorithm development. It's getting innovative ways of leveraging this exponential capability to derive algorithms that are tied to use cases. So I think those are the two biggest ones I would give.
One of the kind of the points that stuck out to me in some of the public material that IBM has released is the piece around simulators and effectively how simulators allow one to model quantum circuits. I'd be curious to understand that in a bit more detail. What exactly a simulator is and how those are used.
Yeah, so I mean, at a very basic level, a simulator is just literally simulating the operations in the quantum computer. And because of the exponential scaling, actually, you can simulate a 20 qubit system on your laptop, because 2 to the 20th is a big number, but it's not an immense number. Whereas 2 to the 50th now becomes a number that you can't simulate on the world's largest supercomputer. At least you can't today. Simulation is getting improved also. So, over time, I think the highest number anybody's come to today is simulating 45 qubits. Maybe we'll get to 50 or 55 or 60 or something on that scale. But getting to 100, yeah, that's not really likely to happen, just because the 2 to the 100th just becomes such a large number. So yes, simulators are really important for us from an educational point of view, and also to have people explore, algorithm development. But when push comes to shove, you still need to be able to run it on a real system to understand the idiosyncrasies of a real working system. Understand how you do error mitigation and all those kind of things that you can't do on just a simple simulator. Now, obviously, internally, we're also working on other types of simulators to help us build better systems. But when people talk about simulators, they're talking about simulate the quantum system.
You guys at IBM have stated that quantum computers may have the potential to deliver solutions to problems where the data doesn't exist. Fundamentally, that seems a bit paradoxical. Can you explain what that means?
Yeah, I mean, so let's take quantum chemistry, because that's probably the easiest one, right? So step one of the problem is that classical algorithms and classical computers don't do a very good job of simulating real-world chemistry. And if you go on NIST, there's a whole bunch of molecules that people have measured that the best classical simulation in the world really just is bad at simulating. So step one, quantum computers hold the promise of simulating those molecules using quantum information theory and quantum mechanics much better than a classical computer and a classical algorithm can ever do. Step two is now you're building new molecules or interacting new atoms in a way for new materials or whatever. Now that you have a system that can actually better simulate the real world, you can leverage that system to simulate what happens when these two molecules combine, or these two atoms combine to form new molecules, or et cetera, et cetera, et cetera. So that's a situation where you're basically simulating something where you don't have the real world data yet on how that molecule is going to behave, or the reaction rate, or whatever. That's predicated on the fact that quantum systems and quantum algorithms can model the real world better than classical systems can. What they're probably referring to in that quote is that what quantum systems are not going to be used for is digging through petabytes of existing medical research on molecular chemistry to find the one nugget among those petabytes of data that has the most relevance to what you're trying to do. That's where classical systems and things like IBM Watson are really good at. But what they're really not good at, simulating quantum chemistry to create new data that doesn't exist before.
No, I think one of your comments in there was around simulating the world, and it sounds like if I can really distill this conversation down to one key point, it's that quantum computing will help us do just that, simulate a hyper complex world that we as human beings fundamentally aren't able to fully comprehend, and therefore our decision making is necessarily limited, extremely limited. Would you agree with that?
Yeah, no, I think that's absolutely right. And like the distinction that I just made, that quantum computing can simulate very complex situations where the probability space or the possibility space is just exponential and enormous, whether it be quantum chemistry or all the interactions in a country's GDP or financial optimization or whatever. What classical computing will continue to be good at is looking at huge amounts of data that already exists and pulling the insights from that huge amounts of data. So both of them are going to be really important in better understanding the world. But what quantum computing is going to allow us to unlock is understanding the probabilities and the possibilities and trying to find the best one for these really complex problems that society has.
So there, I mean, if I think about, something like a Monte Carlo simulator, which kind of seeks to get at kind of a most likely outcome based on a kind of an uncertain range of possibilities. It sounds like, to an extent at least, some of what quantum computing can do is build on that sort of framework. Does that suggest that results of quantum computations are directional or indicative or kind of bands of likely outcomes as opposed to kind of specific solutions to equations?
Well, I mean, fundamentally what a lot of these algorithms do is find the lowest state or lowest energy or highest energy state of a cost function. So yes and no. I mean, I think it will be done in a different way to try to find what is the best possible solution to a problem. What is the minimum, what is the maximum to a problem statement. Now, there is going to be some level of probability in the calculations for the foreseeable future. So it's a little bit similar, but a little bit different. You're really looking for, what is the minimum or the maximum for effectively a cost function. That's a lot of these algorithms.
Sure. No, well, it's fascinating to think about the potential applications, and clearly a lot of the initial interest, I'm sure, will be kind of commercial, i.e. company X looking for ways to, I think some of the examples you mentioned around financial portfolios, around logistics, around mapping, things like that. But really, it sounds like some of the gargantuan problems that we as humans face, I don't know, around global warming and what the best responses are, around really kind of long-term social and political problems could be supported with the power of quantum computing.
Yeah, I think there is possibilities there. I mean, again, when you got a lot of variables, they all are interdependent, and you have subtle interactions. I think quantum computing, that 2 to the n power, has the possibility to really explore possibility space for those kind of problems. So I think that's true. And in IBM research, they're already thinking about it. And I'm sure as we open up more and more access to these types of systems over the coming years, you will see people start exploring use of them for those kinds of applications as well.
Well, fascinating. Scott, I really appreciate you helping me get to grips with a lot of this. I think we're clearly talking about bleeding edge technology, which has the power to be potentially hugely transformational over time. What's the best way for people to find out more about your work and connect with you directly?
Yeah, I think the best way is IBM Quantum Experience. There's a lot of good educational material there. There is links to if you want to learn more, and that's probably the best way.
Great. Well, Scott Crowder, thank you very much for joining us today.
All right, my pleasure.
Thanks for tuning in to Rebank. If you like today's show, reach out. Follow us on Twitter at Rebank Podcast and join the conversation. For more on banking, fintech, and the future, check out our regular content at www.bankingthefuture.com.